Hello everyone, today I'm introducing the dual piston pump, a vital component in analytical chemistry. Dual piston pumps are a type of reciprocating pump that use two pistons working in sequence to deliver fluid with high pressure and precision. Unlike single piston systems, which often produce an even flow, dual piston pumps minimize pulses by alternating strokes between the pistons. This results in smoother and more consistent output. They are especially important in fields like high-performance liquid chromatography, where stable flow is critical for accurate chemical analysis. Now let's look at the core components of a dual piston pump. The cylinder block houses the pistons and forms the main structure of the pump. Inside, the pistons move back and forth, displacing fluid with each stroke. Fluid enters through the inlet valves during suction and exits through the outlet valves during discharge. These valves ensure one-way flow and prevent backflow. The pistons are connected to the crankshaft via connecting rods, which convert rotary motion from the motor into linear piston motion. To maintain efficiency, the pump uses seals. This includes piston seals and static seals to prevent leakage and maintain pressure. Finally, the drive mechanism, usually an electric motor, provides the input power that rotates the crankshaft and initiates the pumping cycle. Together, these components ensure the pump delivers a smooth high-pressure flow with minimal pulsation. Next, we're going to move on to working animation and the application for dual piston pumps.
First, let me explain the suction stroke. When piston A moves backward, it creates a low pressure zone inside its cylinder. This causes the inlet valve to open, allowing fluid to be drawn into the cylinder. At the same time, piston B is undergoing its discharge stroke. Next is the discharge stroke. As piston B moves forward, the pressure inside its cylinder increases. This pressure forces the outlet valve to open, pushing the fluid out of the pump. Meanwhile, piston A is completing its suction stroke. Finally, this leads to the alternating action of the pump. The two pistons operate 180 degrees out of phase, while one piston is drawing fluid in, the other is pushing fluid out. This overlapping action reduces flow interruption and minimizes pulsation, resulting in a smoother and more continuous. Next, I will explain the applications of a dual piston pump. First, in hydraulic systems, dual piston pumps are commonly used in hydraulic press and heavy machinery. They can generate very high pressure, which is essential for lifting, pressing, and precise mechanical movements. Second, in the chemical and process industries, these pumps are used for dosing and metering chemicals. The alternating piston action allows accurate and consistent flow, even when handling corrosive or viscous fluids. And third, in water and wastewater treatment, dual piston pumps are applied for chemical injection, such as adding chlorine or coagulants, and for pumping sludge. Their high pressure capability makes them suitable for these demanding operations. Fourth, in the oil and gas industry, they are used for high-pressure fluid transfer and chemical injection into pipelines. The smooth flow reduces pulsation, which helps protect the pipeline systems. This is the example how dual piston pumps works.
Now, let's take a look at the advantages of dual piston pump. Dual piston pumps are high-performance units designed to overcome the limitations of standard pump systems. Let's look at why they are preferred in demanding industrial and laboratory settings. First, we have higher flow rate. By utilizing parallel or double-acting configurations, These pumps effectively double the volume of fluid moved per cycle. This allows for high capacity output without significantly increasing the pump's physical footprint. Second, we have improved efficiency. Efficiency is a major factor. Double-acting dual pumps used to return stroke to move fluid, meaning the motor performs productive work during the entire rotation rather than idling half the time. Third, we have reduced pulsation. One of the biggest mechanical benefits is reduced pulsation. By timing two pistons to operate 180 degrees out of phase, one refills while the other discharges. This fills the gap in flow, leading to a much smoother output than single piston models. And lastly, we have lower maintenance frequency. Finally, because the workload is shared between two pistons, the mechanical stress on individual seals and bearings is more balanced. This symmetry helps it extend the overall service life of the pump's components. However, these performance gains come with specific trade-offs. It is important to consider the challenges of this design. Now, let's take a look at the disadvantages of dual piston pump. Firstly, we have increased complexity. The most immediate drawback is increased complexity. Having two of everything, including pistons, seals, and check valves, means that there are twice as many parts that can wear out or potentially fail. Second, we have bulky profile. Because of the dual cylinder setup, these units are typically much larger and heavier. This bulky profile can make it difficult to fit them into compact or mobile machinery where space is at a premium. Thirdly, we have higher costs. Precision comes at a price. The need for exact synchronization and additionally high pressure components makes these systems significantly more expensive to manufacture and purchase than simplex or single pumps. And lastly, we have synchronization on risk. Finally, there is a risk of synchronization on failure. If the timing between the two pistons slips due to mechanical wear or drive issues, it can cause water hammer effects. These are violent pressure surges that can vibrate and damage your entire piping system. So the conclusion is, in summary, while dual piston pumps offer superior flow and efficiency, they require a higher investment in both cost and maintenance. Choosing the right pump depends on whether your application requires that precise, high volume flow.